Hello, everybody. Welcome to a new session of our series of workshops dedicated to the concept of strength in composites. Thank you very much for coming. We are using platform Zoom. I hope to have not too many problems with it. I apologize for any inconvenience in the use. And let's start with the presentation. Okay, as there, for sure, there are people that is the first time that attend this meeting or this series of meeting. The origin came from one European conference on composite material that took place in Stockholm in 2008, organized by Leuven. After the meeting, we led with the leadership of professors Tarreya and Barna, we started a series of damage workshops. In one of them, Michael Wisnom suggested that it would be nice to discuss the meaning of the word strength applied to composites. And then in October 2020, we had one meeting with the name, How do we define and measure strength of a composite? There were many people in this workshop, and we considered that it would be nice to continue. And we had another in March 2021, measuring UD tensile strength and the factors affecting it. Then we had another one measuring UD compression strength and the factors affecting it. And then in March 22, we had the last one measuring shear strength and the factors affecting it. And now we are having measuring transverse strength and the factors affecting it. Now, the previous workshops, you can, in this page, you see that you can get the information generated in all these workshops in the directions you see in this slide. We start the objectives of this series of meetings on the concept of strength. In the first meeting, the general objectives we defined were to discuss the concept and meaning of strength of a composite, to try to reach agreement on a definition of strength, to discuss fundamental issues with measuring strength, to identify next steps to make progress. And with reference to transverse behavior, I think that in this case, we have to identify the difficulties in running tests to determine strength properties under tension and compression in a direction normal to the fibers, to discuss the representativity of the values obtained from different types of tests, to try to clarify the scale effect associated with the behavior in transverse direction, and to visualize the use that the industry makes of properties associated with transverse strength. There are some activities derived from the discussion. In this workshop series, it is intended to continue workshop meetings with activities derived from the discussion. There is one which is being running now, and I will invite after my presentation to give an update of the situation of this round robin to Yentl. Here you have, in any case, the participants in the first round robin derived from the workshop 2. So the agenda we have is meeting introduction and background, where we are now, then the topic presentation, and then we enter into a session of 5-minute presentations with 8 presentations. Then during 20 minutes, the panel members will enter in a discussion, a break of 10 minutes, and then at 3:30, we will have an open discussion where everybody can participate with question and answer or raising hands. Finally, 20 minutes to conclusions and suggestions for next steps. Here you have the list of 5-minute presentation. I will introduce them one by one, obviously. And the ground rules are the following. Session is being recorded. Slides will be shared afterwards. During discussions, write Q and answer at any time. You can write at any time, but they will be answered during the second part of the meeting after the coffee. Or you can raise hand during the second part of the meeting. There are no cameras for the audience, only micros will be open after raising hand. There is also the possibility of using chat, but our recommendation is that you use chat only for general comments or to say hi or hello, how are you, to a friend who is also participating in the meeting. So I will invite now Michael and Yentl to say something in this presentation of the meeting. Michael?
Well, thank you very much, Federico, for a nice introduction to the aims of this workshop. I don't think I've really got very much to add. I think it's really important and interesting to consider the fundamentals, and that's what we're trying to do in this series of workshops. So I look forward to some interesting discussion. Thank you.
Yentl?
Okay, also welcome from my side. It's really nice to see we have almost 90 participants, despite I think the topic getting more and more advanced or more and more specific. I will perhaps say a few more words about the round robin. So you've seen this briefly, that this is linked to the longitudinal tensile strength or workshop 2. So the goal here is to set up best practices to determine which specimen designs work best, but also like which grips work best, how should these materials be cut to get essentially the most reliable measure for longitudinal tensile strength. And the goal longer term is that this eventually leads to a specific ISO standard, specifically for UD composites, in addition to the more generic ISO standard that already exists. So Torre has actually manufactured all the panels for us, and we are now working on preparing all the individual specimens. I just counted this morning, and we have about 500 specimens to prepare in total. So this is really a huge effort, because we have 7 different specimen types that we want to check, and not all the testing labs test every single specimen from these 7 types, but we do have quite a lot of specimens being tested per testing lab. So right now we're still finalizing the specimen preparation, and I would hope that in the next few months we can actually get started with testing, so that in about 6 months or so we would have the first results, which we will of course also be presenting at conferences and things like that, so that it's also shared with the community before it ends up as an ISO standard. And that's it from my side.
Okay, thank you very much.
And just to say that I think that the test methods which are being evaluated were some of the ones presented at that first workshop on tensile strength, and it's going to be very interesting to see how it works out, because ideally if we got good test methods, we should be getting the same results from the different test methods for the same strengths. So we shall see what happens. I think it's going to be a very interesting exercise.
Okay, thank you, Michael. Thank you, Yentl. Let's enter into the second part of the agenda, which is the topic presentation that Yentl, Michael, and myself, we have prepared. Okay. In our first workshop, we defined the strength at the maximum stress that the material can sustain under uniform uniaxial loading and in the absence of other components. We have devoted one workshop to measuring UD tensile strength and the factor affecting it, as well as another devoted to measuring UD compression strength and the factor affecting it, to determine XT and XC. Today we devote a workshop to the determination of transverse strength properties, nominally YT, YC. The reason for having a unique session for both cases is that the tests to obtain these properties present a series of difficulties that are common, or features at least, that are common to those associated with the determination of XT and XC, sharing the same time of features and difficulty: geometry, entrance of the loading into the specimen, presence of nominal singular values of the stress state, difficulty in getting uniform distribution of stresses, etc. Since almost the definition of the test to determine YT and YC, a phenomenon known as scale effect was observed and led to the concept of in situ strength. The representativity of the values obtained from the test had been concentrated since then. More attention than the problem associated with running the test. Sorry. Okay. For this reason, we have tried to invite to this workshop some of the most significant authors that have been involved in the comprehension of this phenomenon affording explanation. A paper that you are able to read it about how do we measure transverse strength of composite as the factor affecting it has been published. So, due to the fact that some people may not be familiar with transverse direction to the fiber test to determine YT, here you have in this slide the scheme of how to proceed. There are different standards. Some are ASTM and some are European standard. With reference to the ASTM standards, the same apply for both cases, although as indicated, as indicated by this arrow, the width, overall length, thickness changes from unidirectional to 0 degrees or unidirectional 90 degrees. With reference to the European standard, you have here a scheme of the specimen that is has to be tested, and some results appear here. On the left-hand side, you have the specimens. The strain gauges are put to determine modulus. We are now interested just in strength. And here you have on the right-hand side, the fiber specimen broken. Typically, what happens under tension is that differences in between the values obtained, we can check either ultimate load or tensile strength can be quite significant. For instance, here you have 34 versus 49. This is typical. And this leads to have coefficient of variation of 15%, which is quite significant. On the contrary, if we move to a compression test, the problem here is much more complicated in terms of the standard. We have a standard compression test in accordance with the same standard used for parallel to fiber direction. This is what appears in this standard, but we use it also for transverse test. And in this case, this is one possibility. The other possibility is this one. In the first, we have the loading entering laterally into the specimen. So the load entered along these two lines. And in the second, in accordance with this scheme, we have two possibilities. One specimen that appear here for strength and one for modulus. This one with the strain gauge correspond to modulus, and this one correspond to the strength and appear on the left-hand side. So this is just to show you that the configuration of the test is not intuitive, and some of the possibilities we have correspond to what the final, the industry, which is the final destinator of the results, ask you to do. In this case, if you check now the strength, determination of the strength under compression, then we see that the values are not so different, and we move to a coefficient of variation much more molar than in the case of tension. So, as a summary, the transverse test presents similar problems to those identified in previous workshop in the longitudinal direction. In the case of compression, premature failure may appear due to the gripping system that produce local stress concentrations very near to the gauge zone. The response in tension is linear and brittle, whereas a certain non-linearity may appear under compression, where an inclination angle of failure of about 55 degrees is observed. Both in tension and compression, a certain dependency of the properties on the thickness of the specimen has been observed. Finally, also in both cases, the typical scatter associated with loading in a direction normal to the fibers appears. This scatter, as we have seen, being more noticeable under tension than under compression. So in all the meetings, I have tried to come with the viewpoint of the industry. In this case, what I have collected from them is that in spite of the similarity of these transverse tests to determine YT and YC, compared with those to determine XT and XC along the direction of the fibers, they are not performed as commonly. In fact, the list of material acceptance tests of major aeronautic manufacturers only considers tests along the direction of the fiber as a requisite to consider the material flight-worthy. I have got from them some numbers. Here you have, this is courtesy of Element Seville, and during a certain period of time, they have checked the number of tests they have performed in the transverse direction, in tension and in compression, and longitudinal, in tension and compression. Particularly, it is very significant, the difference in compression in between transverse and longitudinal, which is 10 times more longitudinal than transverse, which may imply that the industry have more information, get more information to design a component from longitudinal than from transverse strength. Okay, a couple of words about the scale effect. The scale effect can be illustrated with the two papers, the results of two papers very well known by Parvici, 78 for glass, Flax and Coral, 81 for carbon. The apparent strength of a lamina in a 0.90 laminate increases when the thickness tends to 0. So these questions, this fact questions the representativity of the values obtained for YT in a test. Okay, and here you have some references that appear in our paper and also in the in the table of 5-minute presentation. But this does not represent the enormous amount of publications. For instance, if you enter in Scopus and put scale effect composite, you will get this number of documents. If you enter with in situ strength, you find this. If you enter with both scale effect and in situ strength, you get this high number still of documents. We have to say that scale effect cannot be confused with volume scale effect. I hope that Michael will talk about this last and will clarify this matter. So now the point is coming back to the scale effect, and it's a part, in my opinion, important of this discussion is that's the point of the graph, that all the experimental point in both graphs, for instance, this one, this one, this one, this one for glass, or this one, or this one for carbon. Do all experimental points in the graph represent the same damage in the 90 degrees lamina? This is, for me, a key point. And in fact, we can represent this by means of these two images. So at the end, we have the representation of, can be used for Parvici or for Flax results or many other results. So if we are in a thin lamina, the failure we get is this one. If we are in the use of a thick lamina, what we get is what you have on the right-hand side. It's completely different, and I will try in my 5 minutes presentation to clarify this this matter as a part of the agenda, we have to clarify the meaning of strength in a composite when we talk about transverse. So to conclude, the final comments, in a very brief way, the determination of why strengths present similar type of difficulty than the determination of X strengths. Why industry uses these transverse values less than those associated with longitudinal direction? We would like to have an explanation of this matter. The appearance of ultra-thin plies has attracted again the attention of the concept of scale effect and insight to strength due to the apparent delay in the appearance of damage in the 90 weakest lamina of a laminate. The use of thick plies, which is very attractive from the point of view of saving manufacturing costs, opens the question of the negative incidence that the damage in these laminas may have in the performance of the laminates under different loadings. And finally, I would like to conclude with a question. It would be possible to design a laminate in order to make coincident in terms of loading the failure at the same time of the 90 degrees lamina and the appearance of transverse cracks in the 90 degrees lamina? We will try to answer this question, these two questions. In fact, there are two questions along the discussion. And well, this is the end of the second part topic presentation, and we start with the 5-minute presentation. So the first one is cavitation of a thermoplastic matrix for a EUD composite subject to transverse compression. Lucien.
Yes.
I'm going to stop to share.
Yeah.
Okay.
Do you hear me?
Yes, one second.
Okay.
1 second.
Yeah.
Okay.
Okay.
So you, Lucien, or panelists, then on camera and micro. And you can start.
Yeah. Do you see my screen?
We see your desktop. You need to share the particular application.
Okay. It's okay. So I have
No,
5 minutes then.
No,
we don't have your presentation. No, no.
We just
have
see the whole
your-
desktop.
Yeah,
We
You
don't
can see the presentation?
no. We see.
Okay. Try to share again. This is the presentation. Now.
Now, okay.
Okay. Okay. So I will talk about directly about the deformation, damage, and failure of the UD composite rod under Brazilian test, in fact. And the material consists of pultruded composite with PA6 thermoplastic matrix and reinforced with glass fiber. And here at the top left is the rod. Yeah, as here, and the study of the microstructure showed that there is a variability in the fiber contents, also in the diameter of fiber, and essentially also so two populations of voids. The first one is this small void, spherical one, and this kind of needle as noted as macropores. As we have seen it, we have studied the morphology, the size and distribution of these macropores. So we can see here, when we colored in gold the surface of the voids, you can see here that there are a tremendous amount of these voids. And we have also measured the void volume fraction with respect to the radial coordinates of in the rod. And you can see that the gradient of initial macropores inside the specimen. Now, by running a test, the first test on this Brazilian test on this rod, what you see here in the center at the left, at the right hand, is the stress strain curve, where we have superimposed in red the crack depth ratio through the diameter. And as you can see, there's a brittle failure by transverse compression as soon as we have reached the maximum stress. So in order to better understand what happened inside the material, we have done some study. The first one is a comprehensive study of the voiding in the matrix, where there is measurement of these voids, supposed to be all of these dots, blue dots. This is we call here the damage or void volume fraction. And we have measured also tracking the nucleation, growth, and coalescence of these voids. And then doing finite element modeling, where we have the void volume fraction as the internal variable in order to have a right modeling of the matrix. Now, the last part would be to have this study. So here's the center of my presentation here. You have for this Brazilian test in the top left, you have again the stress strain curve normalized, and in the second y-axis you have the stress, the crack depth ratio. And then in the bottom row, you have the micro-CT resolution at mid-height and what we can see inside the specimen, whereas in the left hand on the bottom row, you can see a finite element representation of a small square in the center of the road. And here you have the color maps, the maps of the void volume fraction then from the matrix then. So as you are doing this test in CT cells, you can see that as soon as you reach the maximum stress, you can see here at the bottom right that there is a crack inside the material that you can't see at the surface. And also the finite element modeling can see that there is some crack which is parallel to the direction of the compression that appears here. And then doing all of this in situ test with 3D imaging, you can, and also by running this finite element method, you can have this result. So what we can say here as conclusion is that from all of this method, we can have the local as well as the global parameter that you can measure the surface and so inside the specimen. So we can deduce then the strength or everything like this. So this is the end of my talk.
Thank you very much, Lucien. Thank you very much for presenting your results in 5 minutes. Thank you very much. Now, we are moving to the second that I hope you will see soon. Okay, here you have. The second one is transverse biaxial test on long fiber reinforced composite and will be presented by Elena Correa. As always, Elena, turn on camera and micro.
Okay, can you see me?
We can see you. Now we need to see your presentation.
Yes, I'm moving to my presentation.
Perfect.
Wait a minute. Okay, here we are. Well, good afternoon. Thank you very much, first of all, to the organizers for inviting me to join this seminar. The work I'm presenting today, of course, deals with transverse failure, but in the case of biaxial load, we performed a series of experimental tests. So I'm presenting the results associated with this test in tension, and tension compression loads. And although the results will be micromechanical, of course, there should be a response at micromechanical level of these results I'm presenting. Well, the performance of this test is quite challenging, mainly because of the difficulty in achieving geometry free of concentrations. Besides, in this particular case, the orientation of the fiber is also a problem, and it really conditions the manufacturing process. We've got here the stages of the manufacturing process. I don't have time to explain them, but I would say to build cross prints. We need to cure it, and after that we have to cut it into slices, and then a very delicate machine process in order to obtain the final geometry. With this campaign, we obtained some results. First ones were related to the effect of the secondary traction on the failure occurrence. I will share again after a slide containing these results. Second, the orientation of the plane of failure, which resulted to be always perpendicular to the main tension. We also could detect the position of the initial point of failure by means of high-speed camera, and we also performed some strain measurements in the center of the specimen. Well, related to the results in terms of load, here we have the apparent stresses associated with the vertical and horizontal actuators, so that we have divided the loads provided by the machine by the transverse area of the arms of the specimen. These results, of course, are not any kind of strength, do not represent any kind of strength of the material, because the failure is taking place in the central zone of the specimen where the area is a different one. But this shows a tendency, and that this tendency means that when there is applied a secondary compression, the value of the tension nominal responsible for the failure reduces. As I said, we also measure the strains, the value of the strains at the center of the specimen. Here we've got the result we obtained, the both normal strains, and we detected an apparent also linear tendency. So we took advantage of this tendency and performed a linear regression. And this is the equation that relates the strains at failure, including here in this expression the value of the property associated. Finally, we also performed a finite element model. We wanted to try to reproduce the behavior of the specimen during the test, and it was a successful attempt, I should say, because here we have the numerical expression that can be compared with the experimental one. There's slight differences, but I think the adjustment is really good. The features, the key features we took into account in order to obtain this agreement were based in three facts. First of all, the different stiffness values for tension and compression. We performed some characterization tests in order to measure them. Also, from that test, we took into account the different stiffness values for directions 2 and 3. And finally, we also took into account the nonlinear behavior that Federico referred before in the compressive. So I think this will be all for my part.
Okay, Elena, thank you very much also for attending in the 5-minute time. Okay, let's move to the third one. The third one is size effects in transverse tensile strength, presented by Michael Wisnom. Michael.
Yes, hello. Yes, I'm going to talk about size effects. And what I'm talking about here is volumetric size effects. So Federico was talking primarily about the effect of thickness on strength in laminates. Here I'm talking about the effect of volume in UD materials. So where failure is brittle and depends on defects, then we'd expect size effects. And this is what we've seen in tests on most types of loading on composite materials. And this is indeed what we see with transverse tension as well. So here's some data from Kevin O'Brien, published some time ago, where he took specimens of AS43501-6 carbon epoxy with different widths and a large variation in thickness. And the plot on the right shows on a log-log scale the transverse strength as a function of the total volume under stress. And you can see a very clear relationship with a reducing strength with increased stress volume. And it's pretty linear, which means that because this is plotted on a log-log plot, it means that it follows a viable scaling, and the viable modulus is about 12. And they propose that it was matrix microcracks and fiber matrix D-bonds, which were likely as the inherent flaws which determine this size effect. And we've also seen size effects in interlaminar tension. We tested these, what we call humpback bridge specimens, these curved beams in bending. And when you have a curved beam in bending, it generates interlaminar tensile stresses. And we scale the specimens. So we had 3 sizes of specimens, which were fully scaled. All the dimensions were scaled. And these were carbon epoxy. And as you see on the right, we see a steady drop in the interlaminar tensile strength with increased volume of the material. And this corresponds to a viable modulus of about 19. Now, some very nice work been published more recently by Mike Chabay's group, and what they did was they did work on IM 78552 carbon epoxy, and they developed a new test on the right for the direct transverse tension, which is wasted to try to avoid some of the problems with the test itself. And they also tested 3-point and 4-point bending of the same material. And you can see that there's a big difference in the volume of material. In the 3-point bend, you only have this very small volume underneath the loading roller near the surface, which is subject to a high transverse tensile stress. 4-point bending, it extends between the two rollers, so you have a bigger effective volume. And in the direct tensile test, the whole volume is subject to transverse tension, and particularly this gauge section down here. And they generated a really good statistical data set because they had 36 repeats, at least, of each of those tests. And what you see is a significant decrease in strength as the volume increases. The 3-point bend shows these highest results, and then they progressively decrease for the 4-point bend with a bigger volume and the transverse tension with an even bigger volume. All three sets of data fit the Weibull distribution. So here you see the results of the large number of specimens for each of the three types plotted on a Weibull plot, and they're pretty close to a straight line, which again suggests that these fit the Weibull model quite well. And the Weibull moduli were in the range 12 to 15, which was similar to the other ones that I previously showed. And it's worth also mentioning, I don't want to dwell on it, they also looked at the effect of polishing the edges. And they found a 36% increase in strength when the edges of the specimens were well polished. So if you accept the Weibull model, then you can use the results from one test to predict what would happen in another test. So what they did in this case was to calculate the stresses for equal probability of failure by integrating the stress distribution over the volume, taking account of the variability inherent in the Weibull distribution. And so taking the strength parameters from the tensile direct stresses, then, which was around 80 megapascals, then they were able to predict what would happen in the 3-point and the 4-point bending tests and compare against the experimental measurements. And as you can see, the increased strength that you see with the bending and the higher for the 3-point versus the 4-point were all captured very well. So transverse strength is defect controlled, and therefore we see large scatter and a strong size effect. We see similar size effects for interlaminar tensile strength as for in-plane transverse strength. A 2-parameter Weibull modulus model fits the data quite well and can be used to predict strength. And I think the most important thing from this is to say that we can't use a single deterministic value of transverse strength. And it comes back to something we said right in the very first workshop, that when we specify a strength value, we really need to specify the volume of the specimen from which it was measured. Thank you very much.
Thank you very much, Michael. Exactly 5 minutes. Thank you. Let's move to the next presentation. Here you have this new test approach to determine the transverse tensile strength of carbon fiber reinforced plastic with regard to the size effect. Bodo Fiedler from Hamburg University of Technology. Let's go.
Yeah, thank you very much, Federico. And I think also Michael gave a perfect presentation. So our results fits very well. We will see this in a minute. And our idea, the material is a high performance carbon fiber composite material, as you see here on top. And we vary the thickness of the specimens. So layers of prepreg, and then we made 3 plates from each configuration, and then cut the specimens with a very precise diamond cutter. And the idea for this test was, you see here, it's a little bit shorter. So the length is 150 millimeters, the free length, the gauge length. This is a test when we started, so 90-degree transverse strength, tensile load. And once when we were sitting with a beer in the kitchen, we were discussing, so when the specimen will break, we get the first failure. And so if we use the remaining larger part, or even both parts if are possible, so the remaining part, so this right-hand part, the question appeared, is there a damage or not formed by the stresses here, which of course are not so severe here on this side, to the first failure, so smaller one. And also the idea was then to make a new specimen here from this remaining part. Here we tap new glue new tabs on the end, and then we made again the transverse test, so the second failure. And the question was, what is the tensile strength? So, and from our idea and understanding, the second failure should always be stronger. So the strength of the second should be higher than the first one. Here you see now the transverse tensile strengths plotted. Plotted something wrong here with my no. Plotted here for the thickest specimen, where you here see this red thin line, and as already Federico said in his and presented in his introduction, the scatter is rather large. So these were the standard specimen with a thick one, and then the next ones are the more thinner, more thinner, more thinner. And we see we have really a variety of a large scatter and the strength. So it's not so clear what is here really a size effect or not. Then the black symbols, so the filled symbols here represent from the remaining parts the larger the strength values obtained from the second test. And then we plot also the Weibull plot for both first failure and second failure for all specimens. I have not plotted the Weibull modulus, but I think it was in the very similar range, 16, 14, something like that. And so then we used this data, and now we made the fit, and we took, and I think this is, we took, you know, these were the, where we see the box plots here. These were the standard specimen, just varied the thickness. And then we took the minimum values we got and made from these the Weibull values plotted here in the log-log plot. And then we found the volume dependency in the Weibull plot of 11.17, so which is very close to the 12 Michael just presented. However, what you see here is in the on the left graph that the lower one defines the Weibull plot, so the floor distribution, you could say, so the minimum values. And from these minimum values, we make the plot, and then we could extrapolate to the large value, to very high values for small volumes. And in fact, if you here for the second floors, we can almost reach, in a couple of cases, very high values. So to predict these data, we just need to concentrate. So that was one of the conclusions on the low strength, transverse strength values. And from that, we could extrapolate, or we could fit with a Weibull distribution or Weibull function. And then we could describe the strengths in small volumes. So it's the first failure is at the most critical defect. I think that's not new. And so with this Weibull scaling law, we can predict the transverse strengths for smaller volumes. So that's the outcome we figured out here. Thank you very much.
Thank you very much, Bodo. We are moving to the fifth presentation. Okay, by Mark Flores from Air Force Research Laboratory, experimental analysis of polymer I think it is changed. The title we have. Okay. Se non
All right.
okay, go ahead.
Sorry for that mishap. My name is Mark Flores. I'm from Air Force Research Laboratory. I'm going to be talking about single case studies that I've done, also in addition to the experimental stuff that I've done for the transverse compression. Really, what is a single case study? Well, it boils down to that last bullet. It takes me 5 years to make these specimens. They're very small. They're very critical, and so it takes a long time. So really where I'm at this point is really just one and done, search and destroy. What kind of statistical inferences can we make? A movie speaks volumes, and you'll see a movie later on to kind of understand what those things are happening. But when you think about a single case study, you have to think about what are the requirements for those single case studies? Like, what do you want to observe in order to make some quantifiable assessment? And so these are the requirements. The microstructure under loading must be in the field of view, where fiber locations and diameters can be recorded. And the experiments must be able to capture damage initiation. And also, you know, the very important aspect of it is that can we develop a digital twin of the experiment? So if you could capture all those things, it makes very good information about how to model it as well. And, you know, we have digital image correlation, which could be done at this scale, even effective strain. We don't have the ability to do repeats because it takes a long time, but I'm not opposed to trying different sizes instead. So in many of these cases, I try to do different sizes instead of doing one size and multiple repeats. What requirement is not procuring a uniform stress? These microstructures have lots of heterogeneity, so trying to obtain a uniform stress is kind of hard to do. Performing size studies to validate cross, I don't necessarily do this because we do have some interesting geometries. And reducing the influences of edge effects. I mean, those are important factors, but it's kind of hard to do those things at these particular scales. And so that's kind of where it's going into. And so I published a brief paper, Composites Part A, where we did transverse compressive failure of several micropillars of various sizes. You're talking anywhere from 20 micron by 20 micron by 60 micron, all the way up to 50 micron by 50 micron by like 70 microns. And we've done larger experiments from that. And so from this, you could kind of gain an understanding where damage initiates, propagates, where it, how the influences of fibers affect the progression of growth and so forth. We even did X-ray nano CT to kind of look at where those fibers initiated. We were able to do stress versus strain curves. TC3 and TC4 came from the same column. So if there was a repeat, it would be those two, but their microstructures are relatively different. And of course, at the end of the study, we were able to kind of correlate the properties between IM7 5250-4 and IM797-3 between micro and macro. And to kind of give you an understanding of the experiment, you know, a movie speaks a lot of volumes, just showing these particular transverse compression experiments. We did lots of different sizes to kind of understand where they could be important. To the left is what was published. To the right, we haven't published those things yet because they haven't shown a lot of stuff. But we're seeing lots of pseudoductility at the smaller scales. And as we begin to increase scales, it's become more quasi-brittle. And so the ability to actually image and get to the direct influences of the microstructures is getting harder because the failure is much more catastrophic, but we are getting towards trying to get what those influences are, especially when you're trying to model that. Right now, it's around 65 microns is a rule of thumb, kind of like that transition rate, but more tests needs to be done. That's still under investigation. But we also have the idea of doing in situ nanoradiography. So we put this into an X-ray machine, and we are actually going to the process of doing these studies under X-ray CT so that we could capture every aspect of this experiment and see what makes what influences the microstructure and the failure. And that's all I have. Thank you.
Okay, Mark,
Any
thank you very
questions?
much. We are now moving to Leif Asp, who is from Chalmers University of Technology, who is going to talk about transverse failure initiation at dilatational stress controlled failure event in the glassy polymer matrix. Leif.
Excuse me for the very long title of my talk, Federico. That was unusual. It was almost 5 minutes spent already there. So I'm very happy to have a chance to meet all of you again over Zoom and to talk on this very nice webinar. So many years ago, I asked myself, even before meeting Ramesh, why don't uniaxial tensile test results of glassy polymers translate to longitudinal uniaxial tests in the transverse direction of composites? So if you see in this setup here, 2 glassy polymers that have some significant strain to failure and break.
You need to share your screen, Leif.
Really?
Yeah.
Yeah, that's a good idea. I thought I did. So then that's really then. Can you see it now?
Yeah.
Yep.
Okay.
Oh,
Not full screen yet.
I'm sorry about that, guys. So I asked myself about these unidirectional results for glassy polymers. Why, if we have A and B polymers here, and A has only half the strain to failure compared to B, and if we make a transverse test of a composite with the same fibers of those, it's not necessarily so that the polymer A is weaker than the polymer B in the composite case anymore. So you can have a number of setups here, and there's no relationship between the glassy polymer test and the transverse composite test. And of course, when we use micromechanics, we are kind of advised to look at the uniaxial tensile data for polymers, for instance. I haven't checked if this is true at all for the compressor case, but it could be. So what we found, and when we looked into this, and after joining forces with Ramesh, we realized that the stress state in the composite at any position is everything but uniaxial. And you have zones where you can see here, for instance, that we have high dilatational stresses, and you have other zones where you have high distortional stresses, and anywhere in between you have a mix of these. So typical stress state for a composite, including residual stresses, is tension stresses at the equator here, where you look into a square array of fiber distribution. And for that, we suggested the dilatational energy density based on the first stress invariant. And that was a case that we could prove later on to be valid for any case where you have this tension dominated case. Of course, if you have a shear stress situation, this is not valid. And then one could think about using a test on a polymer under these conditions as a failure initiation value for transverse strength for composites. It's as I'm sure that Ramesh will talk about, it's of course an event of failure initiation, and it's also a failure progression that is following that. And for thin plies, we expect that failure initiation is something that will happen, but we don't see cracks growing. For the thick ply composites, we get immediately more or less a transverse crack forming after failure initiation, and we get these very low strains to failure. So we proposed a test method for this, where we cool down a polymer disc, in this case an epoxy disc, that we have glued between a steel disc and a steel ring. We put that into a chamber and cool that down using liquid nitrogen at about 200 degrees delta T. Then we could see a crack forming from a cavity exploding in this type of polymer. So this is something that one could use as a test to find this stress level when you can expect to have cracks forming. Since this is a glassy polymer, we don't get much effect from the cool down on the strength values. Of course, we need to consider the change in the dependence of strength CTE on temperature, but this can be done. So with this, one can actually apply that on thick-pile composites and compare that to data that you have for those, and you can actually see that with criteria like this, one can actually predict failure, the transverse tensile strength of these composites. Of course, also the von Mises yield criteria, zones where you have high shear strengths, stresses will also similarly do that. So this was my pitch on this, that we need to consider the real stress state inside there to have an understanding on when failure initiates. So I'll stop there. Thank you. Sorry for not sharing immediately.
Okay, thank you very much. Now is my turn. So I'm going to deliver a 5-minute presentation on the importance of micromechanics in understanding the transverse strength concept in composites. So it's a work developed with Maria Luisa Velasco and Elena Correa as a part of the PhD thesis of Maria Luisa. So I have put this because of the year. So I started to be concerned by this problem in 2001, and sorry, I'm not able to initiate the video. All right. So I have put this to clarify that I started 21 years ago to be concerned by this. It has taken me 20 years to start to understand the problem. The importance of micromechanic can be understood easily with failure under tension. This is a very clear image. If we, sorry. If we move to a close view, we notice that the material is heterogeneous. And then the micromechanic analysis of this problem predict that a debonding crack will stop here at the angle of maximum hook stress. Is this corresponding to a direction normal to the applied load? That can be, this fact can be observed on the right hand side. If we move to compression, we notice testing a material that the angle, the parent angle, is 53, 54, 55, as you can see in this image. But there is also a micromechanical explanation. If you take a micromechanical view of the problem, as in the previous case, you will find that the maximum, the direction of maximum hook stress is associated with 53, 54, and you see here how the debonding crack abandoned the interface in between fiber and matrix at the direction, at the predicted direction at micromechanical level of the maximum circumferential stress. When talking about the scale effect, based on this multi-scale model, zero is modeled as homogeneous orthotropic, 90 degrees bias homogeneous isotropic, and then we have a cell where we allow debonding to occur in between fiber and matrix. Varying here the value of n, which implies to increase the thickness of the 90 degrees, as represented here, we notice that representing G, the energy release rate, as a function of the angle, there is no difference with respect to n, which means that there is the same probability of getting isolated debondings in accordance with these predictions in laminates with thick and thin degrees laminate. However, the same probability of getting isolated debondings with thick and thin 90 degrees laminate does not imply the same probability of observing them. In fact, when we arrived to this step of our research, we had never seen isolated debondings, neither in thin nor in thick laminates. I'm going to try to explain on a figure our explanation about this matter. So we put in the vertical axis the deformation applied, in the horizontal axis the thickness of the 90-degree lamina. This corresponds to the interval observed where the failure, the nominal failure, appear as associated with the value of YT. And now this is the prediction derived from our macromechanical study. So there is the same probability of getting this isolated debonding. So if now we represent, in accordance with fracture mechanics, the value of epsilon required to make a crack to expand, this is the evolution showed in the Parvici paper. So now let's consider the two options, thick and thin. If we are in presence of a thick lamina, if we increase epsilon, we arrive to this point. What happened here? There is energy enough to create a transverse crack, but this is based on linear elastic fracture mechanics. It's based on the presence of a crack, but there is no crack. In principle, this is in the pristine state. So if we increase epsilon, nothing happened. Nothing happened till arriving here. When we arrive here in accordance with our previous study, there will be one debonding. Now we have a crack. And now we know that we have energy enough to make this debonding to expand to a total crack. In fact, the difference in between J and K produces an enormous amount of energy to be used in another thing. As you can see here, there is energy to produce a transverse crack and debonding. If we now move here, it's completely different. We arrive to this point and we will, for first time, we were able to show isolated debonding here. If we continue applying epsilon, we have the same debonding plus someone till the moment at which we produce or we find the breaking of the 0-degree lamina. So now this is the last one. Now the question is, what do we understand by strength? If a strength is understood as the abandoning of the pristine state, there is no insight to strength. A damage starts always at the same level of deformation. If a strength is understood as the creation of a damage in the 90 degrees lamina that at least reveals the presence of a transverse crack, then the denomination of insight to strength could be acceptable. And now it's fully understood. Obviously, this has to be made compatible with the definition of strength we established it at the beginning of this workshop series. That's all I have to say. Now we are going to move to the last presentation. It's by Ramesh, the role of local stress triaxiality in determining the transverse tensile strength of UD composites. We are going to run the presentation from here, from Seville. So Ramesh, when you want to move, just tell us.
Yeah, thank you so much. Can you hear me, Federico? All right?
Perfectly.
Okay, thank you. Thanks. And I think I can figure out your scheme. You have placed me at the end because I really don't have much to say. Well, I'm going to make some summarizing comments. I'm not going to show any experimental data. I expected that there would be quite a few observations reported in these presentations. So my comments are going to be, sort of philosophical, asking questions more than answering questions. So let's move to the next slide, please. Okay, I think I already mentioned the word or term strength has to be sort of clearly understood in the sense of what it is communicating. In the engineering sense, we try to say some load-bearing capacity. So as an example, if I have a notched specimen, how much load can it carry? It is not, solid mechanics type of definition of strength. Solid mechanics definition is quite precise, which is if I apply a single component of stress, the material responds to that by deforming. And at a certain point, it reaches a pre-specified criticality. And the value of the stress associated with that is what we can call strength. That is because it's well defined, it can also be measured with some standardization and regarded as a material property. Examples are clearly yield strength that we know from classical times, ultimate tensile strength, and so on. So now if I could get the next slide rather than seeing Federico on the screen, please, can I get the next slide? Hello?
Yeah, we have had problem with the connection.
Okay.
This is the reason why you are looking at me, but we
I
hope.
think Serafin is not connected anymore.
I can try to share. I have it as well.
Yeah, Leif, why don't you do that? You're a good friend. Yeah, perfect. Leif, let's move to, yeah, let's go to the next one, please.
All right, all right.
We are back on track. Okay, so when it comes to composite materials, as I think Federico also mentioned in the introduction, it's a heterogeneous body, which means what we are applying externally on the boundary of it is not what is inside, because as the load from boundary or tractions are transferred into the material, at every point in a heterogeneous body, the state of stress is not uniform, and not uniaction, it is triaction. And because of that, the events that are going to be so-called critical, that we call failure, are going to be different. And depending upon the material, then they are going to be differentiated differently. So if we focus on epoxy or glassy polymers generally, then the first event under applied a uniform tension normal to the fibers has been now quite well established, beginning with Leif's work back in 1995 or so, that the brittle cavitation is the lowest energy requiring mechanism, and it occurs close to the fiber surface when you have multiple fibers, not a single fiber. The next event, as I think Federico gave several examples, depending on what the size is of the thin ply versus thick ply and so on, because brittle cavitation is occurring close to the fiber surface, that the next event is going to be debonding of the fiber. And then if conditions are favorable, it's going to be growth of debonding, kinking out into the matrix, joining other debonds depending on the environment, and forming a transverse crack. When a transverse crack has formed, and I think it has to be very careful, because what we are measuring in an experimental test is the unstable growth event of the transverse crack, because that's when the specimen breaks into two pieces, and we record that. But prior to that happening, a number of things are happening that depend on the local triaxial stress state. And if we don't grab that at those points, then we are always going to be in testing stuck with the final event. And that's not going to be representative of the material behavior. Okay, next slide, please. Live? Yes, thank you. So, yes, please, thank you. So here, just a couple of observations to make. If you look at a practical composite, it has manufacturing-induced variabilities. And as I think Mike Wisnom and others have been talking about, the volume effect is really, in my view, connected to the local material, should I say, variability. That is cluster formation. If you look at the bottom left picture, when there are fiber clusters, the conditions are favorable for the brittle cavitation to occur and debonding to form. And because of the closeness of the fibers, multiple debonds will be able to link up easily. When you have manufacturing defects, they are also volume dependent. They will be the initiators of the conditions of triaxiality that might start out debonding without the brittle cavitation. So on the right, I have sort of repeated what Leif started doing. And I think that inquiry that we began in a teamwork in Sweden, asking why is it that a material like a glassy polymer shows a behavior and uniaxial condition differently than when it is placed inside the composite. I think that opened the door to understanding of the triaxiality of stress state. And in composite materials, that's the fundamental issue. And unfortunately, in testing, it's very difficult to get hold of it. So we had to be complementing physical testing with virtual testing, that is micromechanics, as Federico described. So with this, I think I better stop, and hopefully there'll be a lot of thoughts exchanged in the Q&A session that is to follow. Thank you.
Thank you, Ramesh. Sorry for the problem. I'm connected by cable to the net. Serafin is connected by EduROM, and he has had a problem with the connection. So we enter into a nominal 20 minutes discussion in between panel members. So the workshop is now open to questions and comments of all the panelists. So I ask everybody to turn on camera and micro. So if there is no one with a hand raised, anyone can start. Okay.
Well, so can I kick off and ask a question? Many years ago, I was involved with some work on micromechanics, and we measured the strength of an epoxy, and we measured the strength of a composite made from that epoxy, and they were very similar. But the micromechanics gave us a big stress concentration in the composite, which should have implied that the composite was much weaker than the epoxy. But that's not what we observed experimentally. So I don't know who would like to take that one, maybe Leif or Ramesh. Any comments on that?
If you were to compare strain to failure, you would get a different result, of course. So I'm sure Ramesh is better to answer this than I am, but I think that it can happen that you get the same reading out when it comes to strength value, but what's going on in the material is on the micro scale, not uniaxial. So there will be, by coincidence, that you get this type of result, I guess, when it comes to stress values. But the strain to failure, I can bet that it was at least 5 times lower for the composite than for the matrix.
Certainly, the strain was lower because of the modulus, but it's a curious thing which I've never fully understood. So that's why I was interested in. Ramesh has got any question? When we wrote the first paper, before entering together with Ramesh, the first paper was rejected due to incorrect science. No one was actually thinking about this type of considerations. People didn't like it simply. Of course, sorry.
I think that's the history of my career as well. The papers that I'm recognized for have been rejected twice. It's the third time. So anyway, Michael, coming back to what you were saying, see, if you take the epoxy itself and draw its stress strain curve in uniaxial loading, you get a fairly nonlinear behavior. So you're talking about the ultimate or maximum value in stress, right? If you call that strength.
Well, this particular epoxy was actually fairly linear. It failed in a brittle manner. It was quite a brittle epoxy.
Which epoxy was that? I mean,
it was. Oh, now you're asking. This is 25 years ago.
All right.
921, I think. Hexel.
Yeah, it can be tricky.
Unmodified, fairly brittle epoxy.
Yeah, if it's a brittle epoxy, you know, we are in a little bit of a difficult situation in our interpretation, because what comes in now is a flaw. If you have a brittle material such as epoxy, then its strength, so-called strength, is being determined by flaw growth to unstable growth, right? So there's a different scenario. Actually, what we are talking about is if you have a regular epoxy that's not responding to defects as much. So it is a purely molecular behavior that is showing the nonlinearity. Now, when you put that into a triaxial stress state condition, the same epoxy now becomes brittle because it loses all nonlinearity, because it's all under triaxial stress state. It has no shear. It is equal to triaxial stress state. It has no shear, and therefore all the inelasticity goes away. So I think we have to, the two different scenarios we are talking about.
Okay, first of all, those not speaking, please put the microphone off because I am hearing some noises. I think now it's time for Yentl.
Yeah, I want to comment on this discussion because I think in this entire discussion, you're all forgetting the same comment that I think Bodo is also going to make about in situ strength of epoxies. I mean, when you say a tensile strength was lower of the epoxy than of the composites, how is that in situ strength measured? I mean, the way we typically measure it, you indeed end up with a brittle failure. But if you would make an epoxy fiber and test that in tension, or if you do a compression test, you get from a brittle epoxy, all of a sudden it's very ductile. So this is controlled by the voids that are actually much smaller when it's in between the fibers than when it's tested in large bulk specimens of neat resin. So that's also something important I should not forget in this entire discussion. And then I'll give the word to Bodo. I think he was going to say something similar.
Yeah, thank you, Yentl. Yeah, indeed. So we did these experiments on, I mean, the resin volume in the composite is rather small. So we have to take, even for the bulk epoxy or matrix material, need also small volumes. So then you can get up to 300 megapascals for brittle resin systems. And so it's the balance. I mean, usually the composite has lower transverse strength than the bulk matrix material, or in the best case, it's the same, but usually it's lower. But on the micromechanical level, you can reach 300 megapascals or triaxiality, but the resin volume itself, because of the absence of voids or other defects, is rather high, up to 300 and more megapascal measured.
And I perhaps want to add to this that it's not just about the fact that strength is higher on the micro scale or when you have constraints by the fiber, but it's also that the epoxy is actually far from linear elastic. So the stress concentration that Michael was referring to, that you would expect them to lower the strength compared to the epoxy itself. But in reality, you have yielding, and that's those stress concentrations that you predict based on linear elasticity. They're actually much smaller in practice because the epoxies can yield quite significantly and are far from linearly elastic.
We made thin films of epoxy resin, and so you could observe shear bands.
Okay, any other comment or question for anyone?
Yeah, just a quick addition to this discussion. I think understanding of epoxy behavior helps out if we look at the molecular dynamic simulation of it. So I don't want to advertise my papers, but there's one where how cavity forms in a epoxy is explained much better at the molecular dynamic simulation because the scale is so small. So if you do observations like Bodo is talking about, it is not easy to go down to that scale near the fiber and look at how epoxy is behaving. But if you do MDS, then several aspects of why is it that small volumes produce higher strain to failure versus larger volumes? What's the role of voids? What's the role of interfaces that are formed in a composite? So MDS is probably the way to go. Thanks.
Lucien, your time.
Yes, I have some comments. The first one is that I totally agree with the comments of Ramesh about triaxiality. It has been pointed out that the microstructure is always heterogeneous. And what we can find is that we have the load at the macroscopic scale, and then goes into the microstructure. So then when you are testing even at the macroscopic cell, you are uniaxial. The microstructure is always under triaxial stress state. So we have done some observation about what I've shown you today is a matrix which is a thermoplastic. And so micromechanics, what have been the models that have been done from the matrix was micromechanics, in fact, based on a Gerson model in order to have this the void growth, which is dependent on the triaxiality at the local scale. The problem for experimentalists is that you can't measure the stress in the microstructure, but you just can measure the strain. And the measure the strain, you can have this with micro CT, or even what we have done is in synchrotron radiation techniques, which with a resolution of 50 nanometer. So we can have some results from there. And for the epoxy, we have done with Yentl during the ITN fiber mode, and we have written a paper about this epoxy, where it was supposed to be fair. I would say there's no voids, initial voids inside, but they are failed also, but because there are defects. And there is something which was not expected to see them when we observe what happened. So all of these considerations to say, yeah, you have to take into account the triaxiality calculated by micromechanics if you want to see what happened in the microstructure, and also 3D imaging to obtain at least the strain in 3-dimensional. Just a comment.
Yeah, thank you.
Okay.
Okay, Leif.
Yeah. So I was thinking about thermoplastics as well. So something that turned out quite at the same time as we started to work on these epoxies was I found a paper by Sternstein and Ongshin that was written in the 70s looking at crazing in thermoplastics. And it turns out that crazing also is preceded by cavitation, and you can predict that with similar criteria. So I think the points made by Yentl and Bodo are of course correct, but I think this cavitation occurs in all polymers regardless of the presence of defects or not.
Well, it's good to hear that some of the issues here are to do with size effects, and that we actually see the size effects in the epoxy as well as in the composite. In fact, we did measure size effects in epoxy many years ago, and it was quite a ductile epoxy, but we did find that although the strengths were similar, the strain at failure went up very dramatically as we reduced the volume of material. Perhaps we can just change to talk about compression. I'd like to ask Elena about her compression results, and if you can, it'd be perhaps nice to share the screen if you can, because you showed two plots, and they had where you were showing, if I understood correctly, transverse stress and tensile strength, and there was a slope on that line, and it was very different in the two plots. One of them you showed a marked increase with transverse compression, I think it was, with a slope of 1.4, but then the previous slide before that, it seemed to be much flatter. I'm not sure whether you understood my question there. Was that clear?
Sorry, I thought I was talking. I was muted.
Okay.
What's the slide you refer to? Sorry.
So if you go to slide 5, is it?
Yes.
So there you're plotting. There, if you put a line through the data, that line, it's fairly horizontal. it doesn't seem to vary very much. If I understood what you're plotting there, so you're plotting the biaxial stress state.
Yes, we were plotting, but the referring to the external load. I mean, we took the value that the machine gave us in load at the time that the
Okay.
failure, both in the vertical axis and in the horizontal axis. We divided by that load by the transverse area of the specimens in the arms. So that's why I said this value.
But what I was looking at was that the as you go to the left-hand side, you increase the
where the failure
transverse
occurs,
compression.
Yes. So
and the
compression is
results on the
horizontal.
vertical axis don't seem to change very much compared with the next slide, where you had a very strong slope.
Well, in this case, we're measuring different things. Here we've got stresses, and there's a decrease in the case of compression applied in the horizontal axis. And now we are in the next slide. We are measuring the strains in the center of the specimens. So here we've got the normal strain in direction 2, the vertical one, and the normal strain direction 3, the horizontal one. And of course, this behavior is completely different. This is in the center of the specimen, and we are measuring strains. Here, of course, the Poisson effect must be present. And in the other case, it was only the external values of the loads, so it's quite different.
Well, presumably they're proportional, aren't they? I mean, the external loads would be proportional. I appreciate the strain versus stress, but still, it's just surprised me. I don't know whether that's just my impression, but surprising me that it appears to be a much stronger slope in this plot than the previous one. I know they're plotted the other way around, and that's a bit difficult to compare.
Mm-hmm. Perhaps I should say that it was not that time, but the way in which the specimen, would I say, transmits the load, or the standard loads, changes a little bit from the outer ratio. I mean, if you have, for example, transverse tension in the vertical direction and nothing in the horizontal direction, you will find that in the center of the specimen there is a small compression. So there's slight moving of the curves in from one, I don't know, a state of stresses, external state of stresses, and the inner one. That's the difference. What we found interesting here was this relation between these strains, and what we are working now is in the understanding of this relation, because I agree with you that I don't really know why this relation comes here. So we're trying to do some micromechanics, some models using our values of the external loads, and also combining with this value, these experiments in the strains, in order to, in micromechanical models, understand why this expression is like that. I mean, where's the origin of this relation?
I think we are reaching the time for a break. Just a short comment about this last discussion, because effectively there are representation of some variables in the previous one, force, and in this case there is a representation of another thing taken from another part of the specimen. The question is that it looks like Michael says that both representations are not similarly affected, because in this particular case where we measure in the center of this cruciform specimen, there is a more affectation of the variation with the load applied than when we are just looking at the two arms of the cruciform specimen. This is correct. So let's take 10 minutes, starting now, 10 minutes of break, and then we will start with what is probably the main part of this workshop series, which is to hear what people have to say about what we are discussing. So we will connect again in 10 minutes. Thank you very much for attending this meeting again. Hello, everybody. We are going to start. Hello, everybody. We are going to start with the second part of the meeting. We are going to share. Please put all the microphones off. Please. Okay, thank you. We are going to start with the second part. And first of all, let me share with you what we have to do. We have 10 minutes of delay, more or less, which is not too much. We will finish at 17. And now we have an open discussion with Q&A or raising hands possibilities to participating in the meeting. Then the last 10, 15, 20 minutes will be devoted to conclusions and particularly to suggestions for next steps. Okay, so during discussions, you can write question and answer or raise hand anytime. In fact, I have several questions already formulated and I will go with it immediately. Please use chat only for general comments and saying hi to a friend. Okay, if you want to participate, we are not going to check what is being written or communicating by chat. If you want to participate, you have these two options, question and answer or raise hand. I will have a look of the question and answer. I give a person the possibility to participate, and depending on the hands that we can have pending of participation, we will moderate it in one way or the other. No camera for audience, only micros will be open. We personally, we will do it after raising hand. Okay, so let's start by the questions I have. Okay, I have one question already answered, but I would like to mention here, because one person asked, is it possible to get a record of this presentation? And we have answered, all the workshop is being recorded. The link will be shared in the next days. Okay, now going to questions not answered, I have 1, 2, 3, 4, 5, 7 questions of the same person. The thing is that at the end, the last question is a comment saying, thanks everyone for your thoughts and slides. Bye. So the person has is not now in the meeting. My idea is to give answers to persons that are still in the meeting, and if we have time and someone want to answer these questions, we can go on them. So I have 2 questions from Jose Antonio Rodriguez Sanchez. He's a person who works in Airbus, and I have had a lot of discussion, and I hope to have more discussion in the future with him. The first question is a question for Elena, and says, do we have a quasi-isotropic layup in the center of cruciform specimen? Jose Antonio, if you want to say something in addition to your question, you can do it. It seems that he's not in the meeting now. So Elena, anyway, once
Can I answer?
Yeah,
Anyway.
please.
Yes, well, the specimen is unidirectional. So all the fibers are in the same plane. I don't know if he's referring to the stacking sequence. So we first perform a thick laminate of 108 plies. Well, 2 thick laminates, they were all the same. One of them, we cut it into 2 halves, and then we build the cruciform prints by using the vertical arm, the vertical laminate, the thick one, the first one, and then the 2 halves in the horizontal direction. We use some aluminum blocks, we rip everything, and prior to this, we use 1 single lamina covering the size, all the area of the whole prints, the arms of the specimen, we rip it with the aluminum gloves, and then we cure it. But I don't really know if that was his question. So if he wants to ask again when he comes back, it's perfectly.
Okay, but it's good to reflect the answers in our workshop. The second is for everybody. How do we check that resin content for thinner specimens is the same as per thicker specimens? Who wants to answer this question?
Well, let me just make a comment. I think it's a really good question, and it's one that we've worried about. And I think that for very thin specimens, very often there is a bit of resin loss and the volume fraction may be a bit higher. Going back to the results that I presented on the transverse failure from Kevin O'Brien's work, then the same size effect was there whether he changed the width or the thickness of the specimens. And it went up to quite thick specimens, quite a range of specimen thicknesses. So whilst I think there may be some concerns on very thin specimens, I think that for the thicker specimens, I think it's probably not so important.
And perhaps I want to add to that there are known effects that when you do toe spreading and you make these really thin plies, that you create a more homogeneous microstructure, which inherently is going to be better for transverse strength. But in most studies, when they compare thin versus thick plies, the thick plies are actually multiple thin plies together, so that you at least already eliminate this randomness effect that you have. It's very similar with volume fraction. It in principle then should also be the same, but there might still be more resin bleed out with the thicker plies. That's something that needs to be controlled when you want to do this type of studies.
Yes, in fact, we are using ultra thin plies, 20 microns, 30 microns. And Elena, you can confirm that sometimes the volume of fiber is, the decrease is incredible. So we have, instead of having 35 or 50 or 60, we can reach only 30 or 40.
Yes.
So it's incredible. I don't know if it is the particular case of the manufacturer. We are taking from the material, but this is terrible. Ramesh, I think you wanted to say something. The microphone.
Sorry, okay, just wanted to comment on the definition of the fiber volume fraction. Theoretically, there has to be a representative volume element on which you take the averages. As you go to thinner and thinner plies, the RVE begins to be less and less defined. Say in the limit, if you have only through the thickness 2 fibers, there is no RVE concept valid anymore. So we cannot really talk about volume fraction there. So if you plot something of a behavioral characteristic with respect to fiber volume fraction, it has only to go up to the point where fiber volume fraction can be defined. Once the plies become too thin, their definition breaks down.
And Federico, perhaps also to respond to your point, when you go to these really ultra thin plies, 20, 30 micrometer, my feeling from looking at microstructures from those plies is that actually stretches the manufacturers a little bit too far, and that they cannot achieve consistent quality anymore, consistent ply thickness. So I think those thin plies are not the best to do like really consistent study, because they inherently have too much variability, because the toe spreading gets really difficult at that scale.
Yentl, absolutely, I agree. So we have it because we wanted to check the use of these ultra things. But for us, the minimum that reflect, that you are using a material that have apparently the same configuration. Okay, let's not talk about volume fraction, but the same configuration, that one of classical thickness of 200 microns is 50. With 50, it is reasonable, okay? And for us, it's enough to check if the behavior of laminate having a 50 microns ply illustrate what we want to do. We have found this correct, and for me, it's okay. Less than 50, absolutely. I don't think we can get conclusions from the use of 20 or 30. Additionally, to manage the 20 microns ply to perform a laminate is extremely, extremely complicated. Absolutely, I agree. Elena.
Yes, just to add a comment to what you would have said, I fully agree. But what I think we have seen is that, in spite of this idea that the ultra-thin ply is more dispersed in the fibers distribution, when you test them, you at a microscope find common patterns in every part of this lamina. So it's not difficult to identify the pattern defects in spite of this irregular distribution.
Sorry, I think I have Paul with the hand, but Paul, 1 second. I have noticed that Jose Antonio Rodriguez, who formulated 2 questions, is with us. Is it true?
Can you hear me?
Yes.
Oh,
Please go ahead.
Sorry, Federico. It's my first time using Zoom and in this kind of conferences, and to be honest, I am not very safe using the tool. Correct me if I'm wrong. I have listened that when we are testing thinner specimens, the resin content and the fiber volume fraction is not the same. If it is the case, we are not talking about the same material. We are comparing test results for 2 different materials because we are changing these 2 key parameters of the material. Am I right, or I misunderstood something?
I mean, you are right, but in my last talk, I said that this corresponds to 20 microns and 30 microns ultra-thin ply. 50 for us is similar to the other.
No, I'm not talking about this, Federico. Sorry for interrupting. I'm talking when we are comparing, not in your presentation, in other presentation, when we are comparing test results for what you call scale effect.
Yeah.
Okay. Therefore, my question is regarding the scale effect. If we have one scale effect with thinner specimens, not thinner plies, thinner specimens, and we observe different results, my question is related, do we have the same resin content, the same fiber volume? Apparently not, but this is potentially explaining this scale effect. This is one of my questions. The second one is, when we have larger specimens, do we check the potential edge effects in these larger specimens that could initiate the laminations in the edge that is quickly progressing?
Maybe just to respond to the first question, I think there are some studies where the effect that you are highlighting is an issue, but a well-designed study should use the same plies and essentially just block them together to create thicker plies or thicker specimens. And then the effect should be relatively minor. And certainly the size effects are the more important feature in those tests if everything is done consistently.
Okay.
Can I also comment that in terms of the edge effect, I guess it depends whether we're talking about a unidirectional composite or a laminate. In the laminate, where we're testing a cross ply and we're looking at transverse cracking, it definitely can be affected by the free edge effect. In a unidirectional laminate, then conceptually there's no free edge effect, but defects on the edge are very important. And that's why in the study I showed from Mike Shabai's work, there was a big increase in transverse strength when the edges were polished, because by polishing the edges, you get rid of some of the defects on the edge, and therefore you end up with a higher strength.
Yes, you are right. This is the polishing effect in the edge is quite important. But I have seen some of the specimens that we have M plies with 90 degrees orientations, and in the top, in the bottom of the laminate, we have 0 degrees ply. That's my question regarding the free edge specifically for these specimens.
I'm sorry, I didn't quite catch that. You have one ply on the surface. Did you
Yes,
say?
I have seen some specimens that we have N plies, N 90 degrees plies in the middle of the laminate, and one ply in the top and bottom of the laminate at 0 degrees orientation. And this kind of specimens may have this free edge. I agree with you that unidirectional, we should not expect any free edge effect.
So you're talking about effectively the free surface effect with a ply on the surface.
No, free edge. I have seen specimens with the following stacking sequence: 0, N plies to 90s, and 0.
Okay.
In some other presentation, I don't remember which one. And in such case, we may have free edge effect. Therefore, this goes an influence as well in the scale effect, because at the end, you have free edge. The laminations, we have two asymmetrical sublaminates that is starting to have bending, and the lamination is progressing from
Okay,
the edge
so
to the
it's,
center. Yeah,
it starts to get quite complex, but I think that generally the transverse cracks occur before the free edge. So usually the sequence is a transverse crack and then it delaminates, although at the edge there may be interaction between those two phenomena.
Yeah.
Michael, I have had during 10-20 seconds, I have not been able to hear what you were saying. I don't know if the rest of the people have had the same problem or not.
It was fine on my side.
It was fine? Okay. All right. Jose Antonio, the problem you are posing now is something that has attracted our attention, and I hope to find someone to publish our results. Or maybe I will have the same problem that Ramesh referred to have, and the paper will be refused into, okay. But we can discuss this in detail. You are right. There is let's say an edge effect of not of a big problem, but that originates something that we have found. I don't know if someone else. That is cracks in the 90-degree ply parallel to the fibers of the 0-degree ply. So apparently something that you don't expect to have. Expect to have just cracks perpendicular to the loading. But instead of this, in the 90-degree ply, we have found cracks parallel to the fibers of the 0-degree ply. And the explanation for the appearance of this is based on the edge effect you are mentioning. I hope that to discuss this with you in detail. Okay. I have a hand raised from Paul. Paul, it's a pleasure to hear you, to have you here. I have seen your question is fiber volume fraction is reflected in the stiffness of the laminate. Go ahead.
Into this. Can you hear me now?
Yeah.
Okay. Hello, all of you. Nice to hear from you again. Yes, it was just a comment on the size effect, that it's quite easy because the fiber volume fraction is reflected in the stiffness. So when you measure the stiffness of the thin and thick laminates, if you have the same thickness, then you have the same fiber volume fraction.
Yeah, that's a very good point. It's very easy to
so
confirm
it's very easy to check that and to see the differences. But also when you measuring the differences, you also the strength is reflecting the interface, the sizing effects, the material effects, curing effects. So we did a lot in my time. We did a lot of transverse tensile strength test just to check the aging effects from fibers. And it was easily reflected that it was, when you had aging effects, and it was reflected in TTS in the tensile transverse strengths of the materials. But this was just a few comments, but about the at least about the fiber volume fraction, it's easy to check.
The question I would like to pick up, actually, it was from the chap who's disappeared, but I think it's a general question. He was asking about the size effects in tension and compression. And I'm not actually sure whether he was asking about fiber direction, tensile and compression, or transverse, but we've observed size effects in all the modes that we've tested, and the size effect is linked to the variability. So in transverse tension, we see a high variability, and as associated with that is a significant size effect. In transverse compression, you get a much more nonlinear response, and you might see a bit more variability in strain, but not so much in stress. And so therefore you would expect a lower size effect in transverse compression, although that is actually the one that we have not experimentally investigated. I don't know whether anybody else has done that, but I would certainly expect much less size effect in transverse compression, and that goes with the lower variability that we've seen in some of the results which were presented earlier.
And maybe to add to that, these numbers for Weibel modules that we've seen, they were something like 12, 14, 16, whereas in longitudinal tension and longitudinal compression, I think they tend to be somewhere 30, 40, 50, so much higher values, which means you'll have less size scaling, but you have size scaling nonetheless.
Yes, and it's also quite interesting, you can relate the variability to the size effect, and so a Weibel modulus of 12 equates to a coefficient of variation of about 10%. And of course, experimentally, you have variability not only due to the size of it, but due to experimental errors. But I think in general that there's a consistency between the amount of variability we see and the size effect.
Okay, I have three. Yes, Ramesh, then Mark, and then I have a question that appeared in question and answer. Ramesh.
Yeah, thank you, Federico. I just wanted to sort of add, should I say, more confusion to this point about strength variability, fiber volume fraction, and such. Well, see, when it comes to transverse strength, as we talked about before, the local traction stress state is what determines the first event. And as soon as transverse crack forms, the unstable growth of that is what gives us the measured transverse strength. Now, in all this, as we reduce the size of the or volume of the material, if the fibers are uniformly distributed, no problem, because then we can take fiber volume fraction as a continuous parameter. But that's not the reality. Reality is that fibers are non-uniformly distributed, which means the clusters in the cross-section are the determining areas or regions for initiating transverse failure, which means we must have a representative volume element before we can take a continuous parameter that describes the size of the material in which failure is initiating. So I think some of the issues that we are talking about, being able to have the same fiber volume fraction in thin versus thicker ply, resin amount, and so on, it is very difficult to do all this without actually going on the side and do the macro mechanics or virtual testing, as we've been talking about.
Okay, Mark, please.
Yeah, so I've done a few micromechanical experiments, and I've also had the ability to work with probably over 10 modeling strategies in the past, I want to say 5 years. So they're all unique. So I have lots of different perspectives on this problem. Do edge effects occur with smaller, thinner plies? I'm going to guess yes, because for that smaller sample, 20 by 20 by 60, you have to start looking at what's the appropriate size microstructure we should be looking at. And when you start looking at those values, you could have pseudoductility. You could have aspects about that edge effect that could affect what's going on in that microstructure. And as you scale that up, you're going to get different levels of plasticity, and the models already begin to show that. The ability to appropriately scale your Drucker-Prager model, your Moore-Coulomb model, or whatever model that you're using, all the fracture parameters that you're using are not sufficient enough. And again, the size effects that we're doing is not perfect, but it is beginning to draw relationships in which could be used in micromechanical modeling. Most importantly, like, what is the best size microstructure that needs to be modeled? What needs to be put into that model? All those things make a difference, but modeling at the single fiber level may not be sufficient anymore. You might have to look at whether or not if it's energetic or statistical, behavior, and based on those things, develop the appropriate relationships to help you model this stuff. I don't know if I'm making sense here, but I've learned that all these things are important, like edge effects, size effects. They're very critical parameters for predicting, and even coming up with transitional scales so that you can help relate that to micro level properties as well.
Okay, I have a question in the question and answer file from next to Arefe. I'm going to read it and give him the possibility, or her the possibility of speak if he's interested in doing. The question says, I'm doing on the transverse and UD compression for bio-based composite and found the same failure angle. Does anyone find the same and can share the thoughts? So first, if you want to make some additional comment, you can do it.
Okay.
Okay.
Good afternoon, everyone. Thank you very much for your sharing thoughts and your research findings. I'm happy that I also read some of the reports that has been presented today. I was reading their articles. That's nice to see, to have this. I'm doing some research on compression tests in both UD and transverse direction. And then I was looking on the theory how it happens. Normally, what I found is there is angle deviation from the 45. That's the normal von Mises angle equation from the Morse angle. So the deviation, it says, like, because of friction. Now what I found is this friction effect is equivalently affecting both in the fiber rotation in the UD and then on the cracks in the transverse direction. So I was looking how this can happen, but just looking now if someone has found the same results from their findings, and then if they can share us some of the theoretical background why this happens. Thank you very much.
Okay, I'm sure that Elena, for instance, that performed some tests during her PhD could give an additional explanation, but particularly what, and it is one positive aspect of this
Can you hear me? Because
workshop, is that you can contact her after the meeting and, okay, Elena.
Sure.
Ahead.
Thank you very much. Sure, yeah.
Federico, I'm sorry, I missed what you said because my screen, the net went down, but I heard Mengs to speaking. So years ago, we performed these tests and we performed a macro mechanical model with just single fiber model. And we found that the explanation was just a connection between this macro mechanical orientation of the plane of failure in 53, 55 degrees was connected with the angle in which the interface crack deviates from the interface and goes through the matrix, kinks into the matrix. So at micromechanical level, this angle appears. And in the former presentation from Federico's, he showed that image. I mean, he showed a microscopy of some fibers, and we took it in an optical microscope and kinking into the matrix in this direction. So that I think we performed this numeric analysis both for carbon epoxy and glass epoxy. I don't know which is the case of your material. I don't know the stiffness properties of this material, but in principle, I think the angle should be the same, or should be in that range, over 45 degrees and perhaps next to 60, I don't know, but at this micromechanical level, there's a connection with the crack angle and the macro failure.
Thank you, Elena. I had Mark, I had your hand raised. Is it okay?
Yeah, I could speak to that. I think I was looking for an image, and that's kind of what I wanted to do.
Yeah, I was looking Marcus' report, by the way. Thank you very much for the presentation today. Yeah.
Yeah. So let me see. And I don't. This does not do a lot of justice, but what we're finding out in these transverse compression experiments is that you see a lot of these vertical cracks in the matrix as you begin to apply the load. So what's happening is you have the bonds and you have vertical matrix cracks. So the 45, so it all depends on the distribution of fibers and relative to, so if you're looking for mechanisms, and I'm guessing that's like a mechanism that you're trying to figure out, you have a debond followed by a vertical matrix crack. And so it's a combination of debonds and vertical matrix cracks that coalesce together to form that, what you would call that 53-degree angle. And so if you had a different distribution of fibers, you could probably get, different degrees for sure. But that is what I'm seeing in many of these transverse compression experiments. That's what I'm seeing is this combination of vertical cracks, and you can see them in each of these things in concert with the bonds. And that's what's causing the formation and shape. Of course, when it all fails, it goes everywhere. But that would be my assumption that's what's causing the angle.
Okay, first Yentl and then Michael.
Yeah, I just wanted to add a comment on this question. I think there's quite a lot of studies and even YouTube videos from these science YouTubers that show that you have a similar angle also when you do this in granulate or basically in a box of sand. It also tends to fracture at a certain angle. I don't know specifically what that angle is, but my guess is that it might actually be exactly the same angle.
Yeah, it's around 53, 54 angle.
Well, I think this is a really interesting question, and I was going to raise that as well. But actually, can I just first ask, in Mark and yours, it doesn't look really like 53 degrees. And also, Lucien, I was going to ask you what the angle was in yours, because neither of them particularly look like 53 degrees to me. Any comments?
Look, to me, the main concern is that we found an explanation for the 53 degrees, but only works for fibrous materials. And as has been said, this angle appears in non-fibrous material.
Yeah.
So I have not taken, I have not found the time to investigate what happened in non-fibrous material. But in our case, there is a consistent explanation. This is everything I can say.
Well, but this was, I think, the other question I was going to ask.
Mark is sharing.
Sorry.
Is someone sharing?
You want me to stop?
Mark? Yeah. Go ahead.
Okay, I'm sorry. All right. So you could, so so these two pillars are somewhat statistically the same. They came out of the same microcolumn. So that fiber went all the way from here all the way to this point. There's subtle deviations though. Just slight rotations, very subtle. But for the most part, they're similar. And just even though you had the exact same curve, you have different morphologies of cracks. Here, it does look like a 53. Here, not so much, right? So the image that I showed you in the previous channels, yeah, it doesn't always equate to a -53, but the distribution of fibers will definitely dictate the shape and pattern of that crack, is what I was trying to get at.
Okay, I think Elena wanted to say something in this concern.
Yes, sorry, but I couldn't raise my hand. I don't know why. So I was trying to say. Yes, I was very much interested about what Mark showed, because I wanted to ask him about this vertical cracks, because they really surprised me. Because our experience at experimental micromechanical level is completely different. And so I don't know if it depends on how we do the experiments, or because he then connected with the 53 degrees in a I would say in a zoom view, when you get far away from the image. But we never found vertical cracks. And I wanted to ask him if it's something directly appearing in the matrix, or it's the angle in which a crack deviates from the interface. It's an independent event, or this is really connected at the same time.
Oh, you want to know the chicken or the hen or egg kind of
Yes.
scenario. What happens first? Is it a debond or is it a matrix cracks?
Yes.
And we don't know that yet, but I think I have an answer to that. It won't be done in the next 5 years. So I apologize. It's all, I want to say it's all random. In many cases, I just need a nice, kind soul to look at these images very closely as we put loads. I want to say a debond happens first, and then sorry, so I got a meeting. Start my video later. Okay. I want to say the bond happens first and then matrix crack. But again, there's so many of these specimens that I've seen that a crack could happen somewhere else where the bond happens at the same time somewhere else, and they're not completely the same, but they happen in different locations at the same time. So I don't know which one happens first. So there's still more to be determined by that. We are doing modeling to kind of help with that, like what happened first. And predicting failure is more difficult in microstructures than we've ever seen before. So there's only a few people who could do it very well. I'm not gonna lie. And so we're using modeling to help us with that.
Yentl.
Yeah, I perhaps want to add to that in the test that Mark is doing. I believe, if I remember correctly from the paper, Mark, that you do this with focused ion beam milling. And what I've seen very often when they do these micropillar that are focused ion beam milled, that it creates a layer on the outside which is full of these gallium or xenon ions, and that embrittles the matrix locally. And of course, what you're looking at here is the surface. So this sort of building in of these gallium or xenon ions could actually make it more brittle and create a slightly different way of fracturing than what you would expect from other types of experiments which are not affected by this artifact. If it's present, I'm not saying it is, but it might.
Yeah, you know, there was a study by Israel that looked at gallium infiltration of composites at this same scale, and they found that it wasn't a significant difference between the gallium versus other ones. And I forgot how they did it, but they did do that. When we perform X-ray CT, that will be the way you can find if there's density differences, right? So you will be able to pick up on density. So we did do some X-ray and some of these microstructures, and we did see some small density changes on the surface, but they were so minuscule, to say the least. It was hard to determine whether or not it was a density change or just a Rayleigh scattering effect of the X-ray itself. we have been asked about that a lot of times, like how does the fibbing process affect the properties? Well, we did the test, they were somewhat measurable to a micro level test. We said it's okay, but characterizing the effects of gallium is not an easy task for sure itself.
I would not know how to do that. It's
I don't know how to either.
Okay, Michael.
Yeah, I'd just like to come back to this point that Yentl raised about about what happens in granular media. So there's a paper published many years ago by Bajanov applying that argument to composites and saying that the issue is that the shear strength, because the compressive failure is essentially a sort of a shear banding type failure, and the compressive strength, the shear strength goes up with compression. And therefore, if you look at the angles, then you've got, as you change the angle, you've got variation in the shear stress, but you've also got variation in the shear strength because of the degree of compression. And he postulated that failure occurs on the plane where the ratio of the shear stress to the shear strength is the minimum. And that happens to be around 53 degrees. So I mean, it's very interesting. It's a very different explanation. But it also seems, I mean, maybe they're both important. I don't know, but I'd just like to raise that. Are these two explanations linked, or is one of them wrong, or what? I don't know who would like to comment on that. Elena, possibly, or I don't know.
Okay, it is a pity that Bodo has had to leave, because I have a question which has been motivated by his presentation, although it's an open question. The thing is that whereas we are talking about failure in the direction of the fiber, the failure is complete and so on. When we talk about the failure or the damage in the transverse damage in the 90 degree, you have a sequential appearance of transverse cracks. Okay, looking for properties in along the interface between 90 and 0 degrees, we perform a test checking for the appearance of the first crack, transverse crack, and then a second. Okay, apparently, considering that you are in the second case far from the first, so Sembenant can be applied. You have similar stress state. When you increase the loading, you should have immediately, almost immediately, the appearance of the second, but it doesn't work. So sometimes you need to apply 30% more of loading to get the second. And now the question is, if we have to tell one person who is designing a component, but many authors said, okay, I forget about the first, because the first is associated, okay? And now, if your second, and then third, fourth, all continue, the property of the material is that associated with those cracks that have a very small increase of interval of deformation. So the question is, when appear one at the beginning, is this a property of the material? Is this what we have to transfer to the designer of a component, telling him, design the component without overpassing this value? Or should we forget this value because it's associated with that effect, and then to say, okay, the other is the property you have to take into consideration? What's your opinion?
I don't think you can answer that question without specifying for what application. In some cases, a single crack is fine. In other cases, a single crack is catastrophic. If you're talking, for example, about gas permeability, you probably don't want to have any crack. But if it's for structural performance or residual properties, that one crack is not going to matter that much necessarily.
Yeah, I agree. And I think this is linked back to the question that we had earlier about why industry doesn't use this. So in many cases, industry is using laminates, and transverse cracks are perhaps not so significant. And you've probably got them there anyway because of residual stresses. And actually they help in terms of notch strength. They actually improve the load distribution. However, if you have applications where you have large blocks of unidirectional material, and that is sometimes used in turbine, wind turbine and helicopter blades, then these can be really important, and then you need to worry about it. Or another case, in my experience, the airframe people are more concerned actually with interlaminar failure, because a through thickness failure you can get in the corner of a spar or something, and that can be really serious, whereas an in-plane transverse crack may not be so important.
Any other comments? I think Elena want to say something again. Elena?
Yeah, sorry, I missed net again. It's a disaster. I wanted to say something connected to what Michael said before about this combination between compression and shear. But if we are in this discussion, perhaps I could discuss it with him afterwards.
Federico, maybe I want to raise a point that we have raised several times in these discussions. And this is the story about whether transverse strength, whether it's in tension or compression, whether it's a material parameter. And I think here, from all the discussions, it's quite clear that it's not really a material parameter, because it clearly depends on the ply thickness, and that means it's not a material parameter. But if we go back to how we tried to solve this with tensile strength, for example, there we said the material parameter is essentially the two parameters of a Weibull distribution, which that is something you could perfectly also apply here, I guess. You could also say the material parameter is the Weibull shape parameter plus the Weibull scale parameter. So you have two parameters determining your material completely. Any thoughts on the applicability in this particular case of that approach?
Well, I think the results that I showed from Mike Chabai's work indicate that scaling actually works. If you take the two parameters from the transverse tension, you can predict the bending strength. So, but another point to make is that in the first workshop, we actually slightly backed away from that, because we also said that we don't really want to specify material properties which are dependent on a model. So what we concluded really was that we need to specify the volume at which it was measured, and then somebody can use a Weibull modulus, a Weibull model if they wish, but it doesn't require it to be. They could be used an alternative model. Although for this case, it seems that the Weibull model does work quite well.
Yeah, Yentl, I would say, you said, okay, because depending the strength depends on the thickness. 1 second. What do we mean by strength? Because, I mean, this is the objective of this series workshop. So, damage and failure has the same meaning for us. For me, damage is the abandon of the pristine state, something. As soon as you have something by the triaxiality of the stress in the matrix or the bonding between fiber and matrix, we have damage. Failure, for me, have a more advanced level. So it's something that may affect. It's just philosophy. So it's failure is something that may affect the performance of the component. So yeah. In this case, if we talk about the appearance of damage appear always at the same level of deformation. The problem is that we had no possibility to check this experimentally till the appearance of ultra-thin plies. With the ultra-thin plies, we have seen this is correct. We have seen. Before using ultra-thin plies, we had never seen experimentally these debondings, which is damage. But it's failure. I would say, if I'm designing a component, I don't care if I have 3 debondings in the 90 degrees ply. And this is what people that are designing components, my friend from Airbus, they have to consider. If they put very thick laminas, the manufacturing is cheaper, but they may induce large damage that becomes failure because it can affect other external actions. So we test under tension, but then in the component in the aircraft is working under shear, under torsion, under bending, and the damage originated by the failure of one 90-degree ply can affect the performance of the laminate.
Yeah, but I think most people here will agree that if you have some subcritical damage like these small D-bonds, that's not considered that's the strength yet. I mean, in the end, that's something you have in pretty much all the loading cases, even in the one where people think that is very catastrophic and unexpected in longitudinal tensile failure. It's very well known that you have a bunch of fiber breaks well before the actual failure event. So that also applies to all the other loading cases, I think. So I think to just look at when there's a catastrophic event where you have a crack that grows to the entire thickness. In transverse cracking, it sometimes also it has to go through the entire width. That gets a little bit trickier because at which point, if it has traveled through the thickness, do you consider it completely failed, or does it have to travel through the entire width as well? That I think is a bit more complicated discussion to have.
This is true. It's much more complicated. Anyone? Any question? Still have 8 minutes for discussion. I have one for Michael. Michael, you showed us some results you got in 95 about the variation of the property with the volume. Okay, I think it was the first slide. Now, my question is, do you think that the result would be the same with actual materials? So the manufacturing process, the actual manufacturing processes, in principle, warranty that the level of defects has decreased. So if you repeat the test, would you have now with an actual material, what would you expect? To have the same results or different results?
I think in principle, the same results, although the variability might be different. But if you look, okay, with that 1995 study with the viable modulus of 12, with the IM 78552, which is a much more modern material, not that modern, but more modern, then with Mike Chabai's study, he got a viable modulus a little bit higher, about 15. So, so yes, that's a slight reduction in the variability, but the same effect.
Maybe. Any other comment or question before to go to the conclusions and suggestions for next steps?
I have one question, and it's a relationship with size effects, but also the discussion of defects. And I see a lot of people say, oh, well, the only reason why you had a reduction of properties was because there could be defects. But I want to know who has quantified those defects. And that would be a nice study, because I hear about them. I just want to know their influences as you begin to increase your scale, and have they been quantified really nicely in a very nice paper that shows that those are the results of a reduction of properties, or so say.
Personally, I have no answer, but I'm sure that it's affected by your question.
Well, let me make a first comment, and then others might like to comment as well.
Sure.
Well, the first thing is, if you calculate the critical defect size in transverse tension, it's relatively large compared with the fibers. So, so I think that the defect size, it's not necessarily a very specific defect. It's some agglomeration of, I don't know what, it's a pattern of fibers close together or some way and with some other. So it's a higher level defect, I believe, than just a single fiber. And Ramesh might have some comments on that as well. But one other thing, let me say, is that when we were trying to relate the transverse strength of the composite with the epoxy, as I mentioned earlier, we looked for the defects in the epoxy, because according to the Weibull distribution for the epoxy on its own, we worked out what the defect size should be in the epoxy, and we could not find defects of that size in the epoxy. So we took the epoxy and it was filtered with a very, very high, very, very small mesh to eliminate any particles or anything else in the epoxy. It was looked at under the microscope, and defects were not present of the size that were necessary to explain the results. So that led me to the tentative conclusion that maybe the defects in the epoxy come down to the way that actually the cross-linking works, and defects that really at the micro level within the epoxy rather than necessarily macro defects. I'd be very interested in comments on that, because that's a bit speculative, but I think it's a very interesting question.
Ramesh. Ramesh, the
Okay, I
microphone.
just unmuted myself. Thanks. I hope I can say something that is adding to clarity rather than adding to confusion. I think our main obstacle in conceptual treatment of composites is the history of metals, non-composites. Because when we talk about defects, when you talk about size effects, when you talk about strength, all of these concepts are really fixated by our experience with homogeneous materials that we homogenize and idealize in our modeling. Here, I think once we confront that composite materials are heterogeneous, then we must immediately ask ourselves, do we have a measure of heterogeneity before we go to something that we call measures of defects? So, I've been writing here and there, suggesting some new terminology, because I think the use of terminology is important, because otherwise it becomes an obstacle in communicating our thoughts. So strength, as an example, I already made some comments on that. When it comes to defects, as Mark is saying, you need to have somebody tell us, what are they and so on. So the concept of defect severity is associated with heterogeneity. If you have a homogeneous material with uniform distribution of heterogeneities in it, then you don't have the heterogeneity measure anymore, don't have to worry about that. But in composites, we don't have that. That is, fibers are hardly ever uniformly distributed. So the first thing we had to start with is to quantify the deviation from a uniform pattern of fibers before we make any progress. Having done that, then we go to the next level of defining defect severity, which is other type of manufacturing-induced undesirable entities, such as voids, dry areas, misalignments, and what have you. So I think step by step, as an example, if the fibers are misaligned and we are only talking about tensile forces, then we don't have to worry about that. But in compression, that is a highly critical defect severity. And to quantify that is really important, and it's being done for compression. When it comes to shear, there are other issues and so on. So I think having laid down a strategy of what language we are going to use, how we're going to define it, the strength, I think we are confusing ourselves by talking about in situ strength and size dependency of strength and what have you. I mean, if strength is a material property, then it does not depend on anything but the material given. So we have to first fix that. And I think what Federico is suggesting, if you go to ultra thin plies, you reduce the distractions of the size effect, and you go towards the ideal state of as the material performs itself. Once we get that material property from, say, the thinnest plies we can make, then we can start to look at what is the effect as we introduce more and more volume, which captures more and more irregularities, deviations from ideal states, and what have you. And this way we can grow our description of strength. Having found the ideal strength, we can talk about how it's affected by other factors. But I don't like this in situ strength as an example. I don't know what that means. Either it's a strength or it's not a strength. How could it be in situ versus not? Okay, I better stop here because I'm rambling now. I can hear myself.
Okay. Just I would like to add that, I mean, hearing what Mark had, I think, had in mind, I have devoted most of my attention to study the mechanism of failure or the mechanism of damage, how they start, how they progress. For me, to study this, to try to understand the behavior of a real component, I have no need to consider the presence or not of defect. But if you want to predict the behavior of a real component, of course, you need a law or something that represent the presence and distribution of this defect, with the example that Ramesh has given with reference to the lack of different orientation of the fiber under tension and under compression. But to understand the mechanism in itself, with your model, with, I think, till present moment, I have been able to understand maybe the reduced number of mechanisms I have understood, but those I have understood do not require the presence of defects. I don't know if this is or not connected with your original thought. I think Leif.
So I just want to maybe comment on Michael's question. I think also maybe supported by the molecular dynamics modeling that Ramesh and his team presented, that indeed this free volume in the polymer is what is there and present enough to cause this cavitation to expand. I have, of course, it's difficult to look at this in situ. We tried, and there was a guy called Lindley who did tests on this with glass type of substrates, and bonded a rubber type of ship between these glass rods, and looked into the microscope when pulling, and could see these cavities growing in the rubber. So I think that you don't need much of a defect to have this happen under these circumstances. Maybe it's akin of what you see in carbonated water or something, where you see these bubbles with an internal pressure in some way forming and actually taking off. But that's of course speculation.
Okay, so we have entered into the last 20 minutes, and in accordance with our agenda, we should start to establish some conclusion. We have never done it in direct. And the second part of these 20 minutes are suggestions for next steps. For me, this is of particular importance in this meeting, because with the first, we just share concerns about the meaning of strength and so on. And then when we started a series of tension in the direction of the fiber, compression in the direction of the fiber, shear, and now transverse in the longitudinal transverse property under tension and under compression, I think we have finished one cycle, I think, because there are more things, obviously. We can talk, and Yentl, Michael, and me, we are asking you, please, for suggestion on how to continue. We have our own ideas, but of course, if the first was tension in the direction of the fiber, the second obviously should be compression in the direction of the fiber. But now we have to move either to fatigue or to influence of ambient conditions, or many other topics. We can say, no, behavior after impact. Is the strength appropriate for this discussion? So we, Yentl, Michael, and me, we would appreciate very much if you could say something about how you can see the future of this damage workshop. Our first intention with the first one was to say, okay, let's do one exercise. Okay, but Yentl has explained how difficult it is to do it. We cannot do it for each. We would need some funds to do it. Of course, we can apply for funds to the European community or to the countries itself, but for many reasons, I think we are at a point where we need to have some decisions for the future. And we hope to hear you during these 15 minutes that we still have. What do you think, please? Ramesh.
Can I just start out? The most logical extension of these workshops would be to now look at combined effects, right? So you'd, I think that can take another, I don't know, 4, 5, 6 workshops, because we will then be entering the world of how to describe failure theories, because that's the main idea in failure theories, right? To in a general state of loading, how does failure occur? So I think right now there's such a tremendous confusion, in my opinion. Again, it's because of our metals thinking. You know, when we were doing von Mises criteria and such, I mean, we were explaining and learning in our early years before we got into composites. Our mind was fixated into describing, say, the failure in terms of a continuous curve, like a von Mises, which describes interaction. Now, since we are understanding mechanisms in different loading modes, it is clear that there's not a single mechanism like yielding, right? The slip process in yielding. Because if there's one mechanism, you can follow or track that mechanism in any condition of loading, only tension, only compression, only shear, or combinations of those. But what we have learned now from these workshops is that each of those loading modes, axial tension, axial compression, and so on, have their own mechanisms. These are characteristic mechanisms in those loading modes. So when you combine them, you cannot expect a single, even in one quadrant, a single curve to describe those. So I think the next step, hopefully, if we continue to take one pair of the combined loading and focus on that, and then clarify whether or not we can come up with a description of interactive behavior. The word interaction, I think, was going to be interpreted differently than what we have been doing for yielding, as an example. For the yielding, mechanism is single, but interaction is in terms of stress field. Here we have 2 different mechanisms. If you take shear and compression, or shear and tension, we have 2 different mechanisms. Each has its own driving energy. And when we combine them, it is not a simple matter. So I think if we can think of workshop, next workshop, just take one pair of combined loading and focus on that, and see what have we learned from experiments, from micromechanical modeling, from virtual testing, and how do we go further.
Okay, I have Mark and Leif. Mark.
So we, in our team, I mean, I'm glad people are talking about triaxialities here, but it doesn't have to be biaxial. You could design tests with specific triaxialities, right? If it's 0, it's shear. If it's 0.33, that's tension. But what if you start engaging in different triaxiality modes? And what you're trying to do here is design an experiment with any given triaxiality state of stress that you think that aircraft might undergo. And again, you could design experiments this way using shape optimization, topology optimization, basically get materials fail in specific triaxiality states of stress so that you could get specific phenomena. And we're on that approach trying to investigate those things, which is really nice. And when we perform the test, it says what we modeled as well. So it goes both hand in hand. It's not a failure criteria, but it is, you're targeting specific states of stress so that you could get specific phenomena.
Leif.
So I'm again thinking of what Ramesh said. First, he said that we need to accept that we increase complexity, which is causing problems for us. Then you also said that you would like to identify cases where you should focus your modeling exercise, for instance. So maybe what you're actually asking for is a way forward on model experiments and model tests. So where you know the interface, you know the properties of the constituents, and you know the orientations of the distributions of materials. So maybe across these tests that you have handled over these five workshops, there's always a need for a model experiment that one allows it to increase complexity with the limited unknowns.
Michael, Yentl, you want to complete?
Yeah,
some
so
ideas?
I think Ramesh's suggestion is a very interesting one. I think there's a couple of questions. I guess you've got quite a lot of combinations there if you pick a pair. But I suppose if we focus just on the effects of stress on the main principal fiber direction failure, which is what industry really worries about, then I guess we've got 6 combinations. So that's still quite a lot. And the other thing I would say is that it's extraordinarily difficult doing good experiments to get that. And so there's a real paucity of experimental evidence, but I think it would be really interesting to review it, because I agree with Ramesh. I think that would be really helpful and important in making some progress.
Yeah, I think those are indeed interesting suggestions. We should sit together with the 3 of us to see where we think the biggest interest from the community would be in. And in some of the suggestions, we also have to be careful that there's sufficient speakers that we can attract for that there is sufficient activity in the community, that we can have a nice program around this. I think in any case, now we have done really basic strength of UD plies. We're not going to be able to continue that. We have covered all the basic strength parameters, so we're going to have to go to more complex parameters, either combined loading or other loading cases. We've not talked yet about interlaminar fracture, for example. Federico mentioned fatigue, compression after impact, penetration impact resistance. There's many other types of tests on composites that are done very frequently, and all of them face experimental challenges. There's no single test on composites where everybody agrees on how to do the test and how to interpret the data. So there's many different options here. It's good to hear these suggestions so far.
Yeah, I think till present moment, it was reasonably easy to put together 7-8 people that had previously worked on the topic. And then this was a scenario in which to share ideas, experiences, suggestions, but combining loading is probably the next step, but this is much more complicated. So till what point are we in a disposition to say, okay, I have time and I have money to do some tests or to conduct some common activities? This is much more complicated now, and we have to, we all three, we have to take a decision. And for this reason, we wanted to hear what you may suggest about this. The other question is, what do you expect of this series? Is what you are getting satisfying your expectations, or you expect something else? Because there are people asking for, I don't know, are you going to publish this in a place? Are you going to take advantage of the knowledge you are acquiring to produce something? This is not easy, but it is also an open question that you may or not comment. We are approaching.
Federico, can I comment on that? As we know, the strength workshops are sort of the outgrowth or byproduct, or whatever you may want to look upon it as, of the damage workshops that we started, as you mentioned, in 2009 or something like that. So one of the outcomes of that activity was to put together a volume, and you know that modeling, whatever is called the modeling of damage and failure of composites. At that particular, now it's going into 2nd edition, and we are all trying to update our contributions. So that was one way to bring out a focused thought process by experts, and each of us wrote a piece. Of course, it's not still very coherent, but it's better than totally dispersed outcome in journal papers and other places. So we may want to consider something similar here. For instance, Yentl has already been reporting the huge activity of tensile testing in the fiber direction. Michael has been doing something. You've been doing something. Well, what we can do, assign a couple of us as editors and define a little bit more tightly as to what we should be writing, and then put that together. As an example, I just give one direction to go in. Can we develop, I think it was Michael's idea originally, can we develop from all this discussion a standard testing method like the ASTM was doing in D30? ASTM D30 committee for many years focused on how to do testing after impact, after this, that, and the other. It's time now to have a fresh look at it from other points of view, because when ASTM was doing that, we didn't have the computational power that we have now. We didn't have the virtual testing results that we have now. And I believe testing today is not physical testing only. It's very difficult to do observations, even though we have made so much progress. But we combine it with micromechanical virtual testing, then it becomes a broadened testing strategy. So if you, as an example, if you focus on some edited book that will bring out pieces that go towards that goal of having a testing methodology, or could be design. I think some of us are worrying about what is all this our activity leading to, because industry still wants a simple formula. They want to just stick a strain gauge and say, is the strain anywhere less than 0.3%, then we are okay. I mean, that's a really very disappointing end of the goal, but we can try to make it more intelligent by going in the direction of design guidelines. If not testing methodology, then design guidelines. And then we can combine those. This is a 10-year plan. How about that?
Okay, Mark, we have 3 minutes. So last possibility.
I've been in D30 meetings and they're just awful. not to say, but they are archaic, they are old, they are pretty much outdated, obsolete in many cases to the tools that are developed now. They don't even accept digital image correlation as a measurement because it's not a metrology measurement in many ways. So if you're doing DIC, it makes it hard. So yeah, but now these tool sets have dramatically increased in the performance, and I agree. We need to somehow shake things up in assessing the material, using newer techniques, especially using FEA to kind of help us design the experiment. We're getting better understanding on how these things fail, how they perform. So yeah, that sounds good, but it's going to be an uphill battle, and as Ramesh said, it might be a decade.
Okay, so thank you very much to all of you for your suggestions. Particularly, Ramesh has given us the possibility to work a lot in the next few years, doing a lot of interesting things. And thank you very much to all of you for maintaining your attention during 3 hours in this meeting. Thank you very much to all of you.
Thank you.
Thank you all. Very good job. Excellent.
Yeah, thank you. And the presentation should be available very soon and the video shortly.
All right. Thank you.
Okay.
Thank you very much.
Bye.
Bye.
Bye.